Friends, welcome to my YouTube channel. Dhanesh here. In this video, I am going to discuss about Markov's decision process. So before starting into Markov's decision process, let me talk some idea about reinforcement learning. See, reinforcement learning is a pure form of artificial intelligence. In reinforcement learning, the agent or machine is used to attain complex objectives. They are goal-oriented algorithms. And in reinforcement learning, if the agent is attaining the goals, they are rewarded. And if the agent is not attaining the goals, the agent is punished. So I will draw a perfect picture to represent reinforcement learning. So from that you can easily understand what exactly is reinforcement learning. Here you have the agent. This is agent. And here you have the environment. This completely represents the reinforcement learning. Here you have the environment, and this is the action. Here you are taking the action AT. This is the action AT, and after the action it is going to, if the agent, as we discussed, if he is performing the action based on the environment perfectly and he is attaining goals, the agent will be rewarded. So the reward, he is getting the reward RT, and he is promoted to a new state ST plus 1. If the agent is failing in his goals, he is punished or penalized, and he remains in the same state. You need to understand, this agent will remain the same state ST. So from this figure you can understand this. Here you have the agent, here you have the environment. Agent is performing the action AT. If he is, by this action, if he is attaining the goals, he is rewarded and he is promoted to a new state ST plus 1. If he cannot perform his, if he cannot attain his goals, he is punished and he remains in the same state ST. So this is what I represent in this figure. See, agent, one who takes the action. See, that is agent, right? Our machines, our, robots, all are agents. See, now, to understand environment, for a human being, social laws and the laws of physics are the environment. We need to act accordingly. In the same way, the agent takes action based on the environment. And if the agent is attaining its goals, the agent is rewarded. That reward, I represent it as R suffix T, and moved to a new state ST plus 1. And the same process, this continues. It's a cyclic process. But if he is failing, he will remain in the same state ST and he will be punished. See, practical applications of reinforcement learning, I can tell it as robotics, health and medicine, economics, chemistry, finance, everywhere we use, reinforcement learning. So now you got an idea about reinforcement learning. Now I will discuss about Markov's decision process. Markov, Markov is a Russian scientist. I can tell you he is a Russian scientist, Markov. See, in the above figure, you can consider I am, little bit getting into the mathematical treatment as well. So in the above figure, agent and environment we are taking as functions. This is a function. Agent is a function And even environment is also a function. You may be familiar with relations and functions. Y is equal to f of x. Y is a function of x. Okay, you know it. See, environment, I can take environment as a function. You need to understand this statement. Environment is a function which transforms action at into a new state and a reward. Into a new state and a reward. So once again, I am repeating what is environment here in Markov's decision process. Environment is a function which transforms, which changes action at into a new state st plus 1 and reward rt. If he is succeeding, if the agent is succeeding in his goals. If he is failing, he will remain in the state st. And in the same way, what is an agent? Agent is a function which transforms a state and a reward. Agent is a function which transforms a state st plus 1 and reward rt to a new action. See, this agent, this is a cyclic process. Once at beginning, the agent attained its goals and he is rewarded and he got into a state st plus 1, and based on that state and that reward, the agent will do the next action. That's very important. So in the same way, we can discuss agent is a function which transforms a state st plus 1 and reward rt to a new action. So this action will be different as the cyclic process continues. The action will change. This action will depends on the previous state st plus 1 and the reward you got. As you know, if you are, even if you are rewarded, you perform well in your company, like that. So that's the way it works. So one important point here is, for the agent, the environment is a black box. That is very important. You need to understand. He doesn't know much about what is his environment. See, for the agent, the environment is a black box. The agent is having very limited information about the environment. Hence, the importance of Markov's decision process comes into picture. Here the important point is, the environment is a black box. The agent is having very limited information about the environment. Here we use Markov's decision process. Now, what is Markov's decision process? You need to understand. Markov's decision process is a mathematical framework used for decision making. So Markov's decision process is used for decision making. It is a mathematical framework used for decision making. In situations where the outcome is partly random and partly under the control of the decision maker. So once again, I am repeating, Markov's decision process is a mathematical framework used for decision making in situations where the outcome, the result, is partly random and partly under the control of the decision maker. See here, the agent, the output, the agent is having very limited control on the environment. The environment is completely random. He cannot control, as being a human being. See, that's what for us as well. We cannot control the environment. It's dynamic. The same thing only for the agent as well. What we can do is we can control ourselves. See, that's the same thing you need to understand here as well. So here, Markov's decision process is used for decision making, and MDP is used to describe the environment for the agent. So you understood a basic information, basic idea about MDP. Next, I want to tell you, to get into the details of the mathematical treatment, I need to tell about another important aspect in this, that is Markov property. What is Markov property? So you know MDP, Markov's decision process, is a mathematical framework for decision making. And now what is Markov's property? So this thing you need in Markov's decision process. So to understand Markov's property, I am telling some philosophies of life. See, one philosophy you might have heard, live in the present. Or you might have heard, yesterday is a history, tomorrow is a mystery, today is a gift. That's why we call it as present. So the same concept only Markov also telling in Markov's property. This is the statement for Markov's property. The future is independent of the past when the present is given. The future is independent of the past when the present is given. If you know the present situation very well, you can predict the future and throw away the past. If you know the present situation very well, you can predict the future and throw away the past. This is known as Markov's property. So Markov's property states that the future is independent of the past. If you know the current state perfectly, the history can be thrown away. And the current state is the sufficient statistics that gives us the characteristics of the future as if we have all the history. The current state is sufficient statistics that gives us the characteristics of the future as if we have all the history. This is Markov's property. Mathematically, we can write it as in conditional probability. You may be familiar with conditional probability. Conditional probability is, we use it for dependent events. If the current outcome depends on the previous outcome, we go for conditional probability. The situation is here same. So we use the conditional probability. Markov's property can be represented as, this is the conditional probability for Markov's property. Probability of st plus 1. T plus 1 is the next state. Conditional probability of st plus 1 with respect to st is the current state, is equal to probability of st plus 1 conditional probability s1, s2, s3, etc. st plus 1. So I have written the Markov's property mathematically. That's all. See, the conditional probability of the next state, the future, with respect to all the states S1, S2, S3, ST plus 1, see, you can neglect all these past states and you can write it as probability of ST plus 1 with respect to ST. If you know the ST very well, the current state, if you know very well, you can ignore all these things, the past. So this is the mathematical statement of Markov's property. Now what is this Markov's decision process? I explained to you the Markov's property. Now I am getting into the Markov's decision process. So what is that mathematical framework? I am getting into that. So MDP, Markov's decision process, MDP is a tuple. Tuple, you may be, we are using it in Python, and in mathematics, tuple is just a sequence of numbers. So MDP is a tuple. this tuple consists of, so what is the tuple? I can tell you, MDP, it is a tuple. It consists of, it's a tuple of state. You know what is the state? You know, we have already explained you what is an agent from that figure. Then you have T. T is known as the, I will explain you, T is known as the state transition probability function, comma R, this is R. Then you have gamma. R is the reward function and gamma is the discount factor. So this tuple contains 5 elements. First one, it is state. From the figure we explained. A, it is the action performed by the agent. We explained. We didn't explain what is T. T is the state transition probability function. I will explain you. State transition probability function. This is T. And R is the, this is R. This is R. R is the reward function. This is a reward function. So MDP, it is a tuple, contains 5 elements, and gamma is the discount factor. What is this gamma? Gamma is a Greek letter, you know it, discount factor. Discount factor. So these things only we are, this is gamma, this is state transition probability function, S is the state, A is the action, R is the reward function. So this is Markov's decision process. It's a tuple, contains 5 elements, state and action, you know. I need to explain, you know, about, you know, T, that is the state transition probability function, R and gamma. So first I will explain you gamma. See, gamma, it is known as the discount factor. So let me start from gamma. Gamma, I told you, discount factor. So in neural networks and gradient descent algorithm, you may be familiar with learning factor. Alright, so its value ranges between 0 and 1. It is the size of the baby steps we take in each iteration. It's somewhat similar to a learning rate. See, gamma, it's the discount factor. Its value also ranges between gamma. It is it's between 0 and 1. It's element of 0 and 1, or I can write it as 0 less than gamma less than 1. Its value ranges between 0 and 1. If the agent is only focusing on present reward, then gamma is 0. So the agent can focus on short-term goals. Even in your life also you will do this, right? If you are focusing only on short-term goals, if the agent is focusing on only short-term goals, then gamma is 0. If the agent is a visionary, if he is planning for long-term goals as well, if he is concentrating on future rewards as well, then gamma is 1. Once again, if the agent is only focusing on present reward, then gamma is 0. If the agent is a visionary and he can concentrate on future rewards, then gamma is 1. So this is all about discount factor. Now I will tell you what is a reward function. A reward function as we discussed, if the agent is attaining goals, he will be rewarded. If not, he will be punished. Based on that, we will define the reward function. I will give you the mathematical equation for reward function as well, because we have the Markov's reward process as well. So that I will give you the equation for Markov's reward process, that I will tell you. So that is a reward function. How do we define the reward function? If the agent is attaining the goals, he will be rewarded. If not, he will be punished. Based on that, we will define the reward function. The mathematical treatment I will be giving now. Now I am giving some more idea about the state transition probability function based on the Markov's property. See, at that time when we discussed about Markov's property, I have given you the conditional probability. The same thing only, it is somewhat closer, somewhat similar. The same thing only we are going to write it. So transition probability, if you are familiar with statistics, transition probability is the probability of transitioning from one state to another in a single step. So what is transition probability? To understand state transition probability function, the function we call it as state transition. It is an element in that tuple. I am explaining all the elements in that tuple. The state transition probability function. This is one element in that tuple. It is the most important element based on Markov's property. See, Markov's property, I told you, Markov's property states that the future is independent of the past when the present is given. If you know the present situation very well, you can predict the future and you can throw away the past. Based on this Markov's property, we define the state transition probability function using conditional probability. So first I will explain you what is transition probability. To understand this term, transition probability is the probability of transitioning from one state to another in a single step. Transition probability is the probability of transitioning, changing from one state to another in a single step. And state transition probability function, I am defining what is state transition probability function, is the probability of moving from state S to the next state S dash. Previously we used it as ST and ST plus 1, or you can use it as S and S dash. S is the current state and S dash is the future state. S to S dash. When the agent performs the action given by the vector A, action is a, it's a tensor. So it's a vector. So what is state transition probability function? Is the probability of moving from state S to S dash when the agent performs the action given by the tensor vector A. Vector A is the action. We already discussed A is the action. So based on this, I can write the state transition probability function as it is T of S comma S dash. This is the transition probability function. It is equal to the conditional probability of here ST plus 1 is sorry, I have to write it correctly. Here ST plus 1 we have taken as S dash. S dash is the next state with respect to ST equal to S, and you need to take the tensor action vector AT is equal to A. This is Markov's. So we are introducing the action A as well. That's all. See, from Markov's property, this conditional probability I have already explained, but we are taking the action as well because that's very important. Based on this action only, we are getting the reward. So this is the state transition probability function. It is represented like this. Some books write it like this also, TSS dash, it's fine. So it is the conditional probability with respect to the current state and the action, the current action, a action vector, the tensor. It is a tensor. So that we understood now. This is the state transition probability function. Here if you see the past, the states like S1, S2, S3, etc., we have thrown away. You know the current state perfectly, you can throw away the past. So based on that only we have defined the state transition probability function. Now I have told you the reward function. I am giving the mathematical treatment for the reward function. So the reward function, as I discussed, if the agent is performing its goals, if the agent is attaining its goals, he will be rewarded, and if he is not attaining the goals, the agent will be punished. Based on that, we will define the reward function and the Markov's reward process. Next is, we are for that, again Markov's equations are there. So this equation we call it as the Markov's reward process. According to Markov's reward process, the how much reward is accumulated by the agent. See, when in this first figure I have drawn, I told you it is a cyclic process. It will repeat. So each cycle, when it completes, he will be, if he is attaining the goals, he will get reward. So he can accumulate more and more rewards. The rewards accumulated, it is given by the it is, sometimes we call it as the return. The rewards accumulated, we call it as the return or reward. We represent it as GT. It is denoted as GT. So return or reward, it is the reward accumulated in that repetitive process. You remember that figure, it's a cyclic one. So the equation I am going to write it for you. It is GT is equal to sigma. Sigma stands for summation. T is equal to 0 to infinity. Gamma raised to T. Gamma, it is the discount factor. Its maximum value is 1 and its minimum value is 0. If the agent is a visionary and focusing on future goals, gamma is 1. And if he is focusing only on the current goals, gamma is 0. So gamma raised to T into the reward function R. I told reward is a function of two things, the current state xt and the action, the current action T, A of T. This is the reward accumulated. So here gamma is the discount factor, R is the R of xt and AT. Xt is the current state and AT is the current action. In integral form, you can write it as integral of 0 to infinity gamma raised to T. Gamma is the discount factor. R is the reward function. That function, it depends on xt and AT. That reward function depends on xt and AT, then dt. This is the integral form. So in this video, so this is all about a Markov's reward process. So I covered Markov's reward process, Markov's property, state transition probability function, then a Markov's decision process, and some idea about reinforcement learning as well. So this is all about Markov's decision process. Thanks for watching.